Hello everybody, welcome to today's lecture on bypass. So, we have now looked at different processes in material balance systems. We looked at recycle, which is a critical aspect in any bioprocess or a chemical industry. Similar to that, there is another process called bypass. So, the term is similar to what you would think of from a literary standpoint. Bypass is basically bypassing a process. So, that is what it is. So, bypass is when you have a stream which skips one or more stages in a process and goes directly to a process down the line. So, this is called as bypass, and this is primarily used to control the composition of a final exit stream. So, if you look at the process shown here, what you see is there is a divider. It could either be a splitter or it could be some kind of a separator which takes out one stream and passes it across the particular step and then mixes it to the output of the process. So, this type of a system is called as a bypass system. So, this again has a stream which is flowing without accumulating. Just like recycle, you have a stream of components flowing in the bypass stream without accumulating during steady state process. So, having taken that into account, let us look at some example problems which gives us clarity on how to approach such problems where you have a process with bypass. So, here is an example problem. In the feedstock preparation section of a plant manufacturing natural gasoline, isopentane is removed from butane free gasoline. The process and the components are shown here. What fraction of butane free gasoline is passed through the isopentane tower? So, what you have here is a feed of 100 kilograms of butane free feed, and that enters into the isopentane tower. Some of this stream is actually taken out and it bypasses the isopentane tower and is mixed with the bottom stream of the isopentane tower. So, now taking this flow chart into account, let us try to perform the material balance calculations to calculate the fraction of butane free gasoline which is passed through the isopentane tower. For this, we need to know what fraction actually enters into the isopentane tower, which is x, and also we need to know how much skips the isopentane tower. So, let us perform the required calculations to get these values. Now, what would be the system we would want to choose for performing these calculations? The first step for any material balance problem is to identify the basis. In this problem, 100 kilograms of butane free gasoline is being fed to the system, which means the basis would be 100 kilograms of butane free feed. So, we will use the basis as 100 kilograms of F. So, we can identify different systems for performing the material balance calculations. To identify how much of the isopentane side stream, which is S, and the natural gasoline which is being sent to the plant P are being produced, we will consider the overall system. For the overall system, we can write a total mass balance and the N-pentane or isopentane balances. Let us write the total mass balance for the overall system. So, the overall system will encompass the splitter and the mixing point and the isopentane tower. So, this would be the overall system that is being taken into account. So, for this overall system, the total feed would be F and your outlets would be S and P. You do not have any generation or consumption because it is a non-reactive process which you are having here, and you also will not have accumulation at steady state. So, this means the equation becomes S plus P equals 100 kilograms. We can also write an N-pentane balance. So, the N-pentane balance would be 0.8 times 100 is the input would be equal to 0.9 times P, which is the output. So, from here we can calculate P as 88.89 kilograms and S would be calculated as 11.11 kilograms. Now, we can choose a different system to calculate what fraction of this feed enters into the isopentane tower, which would be the mass of X from where we have to calculate this fraction. So, for this you can use the isopentane tower as the system of interest. When we choose the isopentane tower, the total balance would become x equals S plus y, where you have x entering. So, this is the system we are considering. So, we have x entering, S is the side stream which is leaving, and you also have y which is the N pentane which is leaving the tower. So, this would be x equals S plus y, and we already know S is 11.11. So, this gives you x equals 11.11 plus y. So, you can also write an N pentane balance. The N pentane balance would be 0.8 times x would be equal to y. So, why did I choose 0.8 times x? What you have here is a splitter, this 0.1 is a splitter. So, because you are splitting the stream which is coming in, you will get the same concentration of isopentane and N pentane in both the streams. So, this means the concentration of N pentane in the butane free feed and the fraction entering the isopentane tower would be the same, thereby you have 0.8 as the fraction of N pentane present in this stream. So, you have 0.8 x which is the input equal to the output which is y, the output is 100% N pentane giving you a mass a value of y. So, using these two equations we can solve for x and y. So, you get x equals 55.55 kilograms and y would be equal to 44.45 kilograms. So, now we need to calculate the fraction which is being passed through the tower. So, the fraction would be x divided by f, which is 55.55 divided by 100, giving you a value of 0.5555. So, the fraction which is being passed through the stream would be 0.5555. Okay. With that we have solved for the required parameters. Let us move on to the next problem. Here is the second example problem. Fresh orange juice contains 12% solids and the rest is water. Concentrated orange juice contains 42% solids. Initially a single evaporation process was used for concentration, but volatile constituents of the juice escaped with the water, leaving the concentrate with a flat taste. The current process overcomes this problem by bypassing the evaporator with a fraction of the fresh juice, and the juice that enters the evaporator is concentrated to 58% solids, and the evaporator product stream is mixed with the bypassed fresh juice to achieve the desired final concentration. You are asked to draw and label the flow chart for this process, neglecting the vaporization of everything in the juice except for water, and you are also asked to calculate the amount of product which is produced per kilogram of fresh juice which is fed to the process, and the fraction of the feed that has to be bypassed from the evaporator. So, now the first step for solving this problem would be to draw the flow chart. As we had done earlier, understanding all the processes which have been given and drawing the right flow chart with the proper labeling will make our calculations reasonably simple. Let us start with drawing the flow sheet for this problem. The problem statement gives us that fresh juice containing 12% solids and the rest as water is entering into the system. So, let us start with that. So, the first flow would be your fresh juice. So, this fresh juice contains 12% solids and the rest 88% would be water. So, this is now separated probably by a splitter, and some of it bypasses the evaporator while the rest enters into the evaporator, and whatever is coming out bypassing the evaporator is mixed with the product from the evaporator to produce the final product. So, now this position would be the bypass. So, this is the splitter. Considering this to be a splitter, you would have 12% solids and 88% water in all these streams. This would also be 12% solids and 88% water. So, the evaporator would have one stream which is the concentrated juice leaving, and you would also have water which is being evaporated. So, let us assume that you have water leaving and only water leaving as given in the problem. You also have a concentrated liquid which is leaving the evaporator. It has been told that the concentrated solution or the concentrated juice leaving the evaporator would contain 58% solids and the rest would be water. So, let us call it 42% water and 58% solids. So, this is being mixed so that you get the final product which is the desired concentration of the solids. So, that would be 42% solids and the rest 58% would be water. So, now that we have all the compositions, let us also label the masses for these flow charts. So, the problem states that we have to calculate the amount of product which is produced for 100 kilograms of fresh juice which is being fed. Hence, we will be using the basis as 100 kilograms and we will use this stream entering as also 100 kilograms. So, the basis used for this problem would be 100 kilograms. Now that we have 100 kilograms entering, some of it is bypassed and the rest goes into the evaporator. Let us call m1 kilograms as the mass which is entering the evaporator and m2 kilograms as the mass which is being bypassed from the evaporator. So, you have m3 kilograms of water which is leaving the system as the evaporated water vapor and you have m4 kilograms of concentrated juice which is leaving the evaporator. So, this concentrated juice m4 is mixed with m2 to produce m5 kilograms of your final product which is the 42% solids containing juice. Now, this gives us the flow chart describing the entire process that has been given to us in the problem. With this flow chart, let us try to solve for the parameters that have been asked for. As I had already mentioned, the basis is 100 kilograms. So, now it is important for us to identify which systems we want to work with. So, as always we will start with the overall system. So, the overall system would encompass the bypass stream. So, the overall system would have total balances which can be written as 100 kilograms entering through the fresh juice would be equal to m3 plus m5, where m3 is the water vapor that is being evaporated and m5 is the final product that is being produced. We can also write the solids balance. The solids balance would be 0.12 times 100 kilograms, which is the mass of solids entering through the fresh juice, and you have solids leaving through the final product which would be 0.42 times m5. So, this gives you a value of m5 which is the final product as 28.57 kilograms. So, for every 100 kilograms of fresh juice which is being fed, we can produce 28.57 kilograms of concentrated juice containing 42% solids. Now that we have this, we can also calculate the mass of water which is being evaporated. So, the water vapor evaporated would be 100 minus 28.57 giving you 71.43 kilograms. 71.43 kilograms of water is being evaporated from the system. So, the next step is to calculate what fraction is being bypassed. So, we have two systems where the bypass stream will cross the system boundary. One would be the splitter which is the bypass stream and other would be the mixing point. Amongst these two, I have chosen to use the mixing point because that would give me more independent equations. A splitter gives me only one independent equation. So, to avoid any chance of higher degrees of freedom, I will use mixing point as the system of study. So, for the mixing point, let us try to write a balance equation for this mixing point. So, the total mass balance for the mixing point would be m4, which is the mass entering through the concentrated juice, plus m2 which is the bypass stream which is also entering the mixing point, giving you a value of m5 which is the final product. We can also write a solids balance. The solids balance would be 0.58, which is the mass fraction of solids in m4 times m4 plus 0.12 times M2 would be equal to 0.42 times M5. We already know that M5 is 28.57 kilograms. So, substituting the value for M5, we have two equations and two unknowns. We can solve for M4 and M2 and we would get M2 as 9.94 kilograms. So, this is the mass of the bypass stream. This implies the fraction which is bypassed would be 9.94 divided by 100, which is 0.0994. So, the fraction of the stream which would be bypassed would be 0.0994 kilograms per kilogram. Here is the third example problem. A stream containing 5.15% chromium is contained in the wastewater from a metal finishing plant. The wastewater stream is fed to a treatment unit that removes 95% of the chromium in the feed and recycles it to the plant. The residual liquid stream leaving the treatment unit is sent to a waste lagoon. The treatment unit has a maximum capacity of 4,500 kilograms of wastewater per hour. If wastewater leaves the finishing plant at a rate higher than the capacity of the treatment unit, the excess bypasses the unit and combines with the residual liquid leaving the unit, and the combined stream goes to the waste lagoon. Draw and label the flow chart for the given system. If 6,000 kilograms per hour of wastewater leaves the plant, calculate the flow rate of liquid to the waste lagoon and the mass fraction of chromium in this liquid. So, what we have is a stream which contains 5.15% chromium is actually being sent to a treatment unit. So, let us call this the treatment unit. So, from the treatment unit 95% of the chromium is recovered and recycled back into the plant. The rest of the fluid is then sent to the waste lagoon as waste treatment as waste which is being discarded. So, this treatment unit has been designed to handle only 4,500 kilograms per hour of the liquid. In case the flow rate of the liquid is greater than 4,500, some of it is removed, anything excess of 4,500 is removed and it bypasses the treatment unit and it is mixed with the effluent which is sent to the waste lagoon, and the combined fluid is sent to the waste lagoon. So, this is the flow chart describing the process. So, we have 5.15% chromium and the rest would have to be water. So, which would be 0.9485 kilograms of water per kilogram. So, we will also write this in mass fraction. So, chromium would be 0.0515 kilograms per kilogram of chromium. So, because this is a splitter which is being used to bypass to create the bypass stream, the composition of the streams in which is entering the treatment unit and the bypass stream would be the same. So, this would also contain 0.0515 kilograms per kilogram of chromium and 0.9485 kilograms per kilogram of water. So, this stream would also have the same composition. So, let the flow rates be labeled as M1 dot, M2 dot, M3 dot, which is the bypass stream, M4 dot, which is the stream which is being sent back to the plant. You have M5 dot, which is the stream leaving the treatment unit, and the combined unit which is leaving would be the M6 dot. So, we do not know the mass fractions of chromium and water in these streams. So, we will call that as X5 chromium and 1 minus X5 water, X6 chromium and 1 minus X6 water. So, the stream which is leaving, that is being recycled back, contains only chromium, and we know that it is 95% of the chromium which is entering the treatment unit that is being recycled. So, here we have the flow chart, and now let us try to solve the material balances so that we can calculate the mass flow rates. So, we have been told that the basis to be used for our calculations is 6,000 kilograms per hour which is being fed. So, this M1 dot would be 6,000 kilograms per hour. So, this means only 4500 can actually enter into the treatment unit. So, M2 has to be only 4500. So, we know that M2 dot is equal to 4500 kilograms per hour only, because that is what the treatment plant can handle. So, we know M1 dot is 6000 kilograms per hour. So, if you were to write a material balance for the splitter, you would have one total balance that you can write for the splitter. So, this balance would be M1 dot equals M2 dot plus M3 dot. So, using this you can get M3 dot as 1500 kilograms per hour. So, we now have M2 dot, M1 dot and M3 dot. So, we need to know how much is M4 dot and what would be M5 and M6 dot. So, for this we can write a balance equation for material balances for the treatment unit. So, if we were to write the material balance for the treatment unit, we can write a chromium balance. The chromium balance basically says that the amount of chromium input would be equal to the amount of chromium output, because there is no reaction. So, no generation or consumption, and at steady state there will not be any accumulation. So, you get input equals output. So, the input term would be 0.0515 times 4500. So, which is what would have to leave through M4 and M5. So, this would be M4 dot plus X5 M5 dot. So, we do not know M4 or X5 M5. However, we have been told that 95% of chromium input is actually leaving us M4 dot. So, we can calculate M4 dot as 0.95 times 0.0515 times 4500. So, M4 dot equals 0.95 times 0.0515 times 4500, which is equal to 220.2 kilograms per hour. So, that would be the mass flow rate of chromium leaving through the stream M4. So, writing the total balance for the treatment unit, we would basically have, substituting this M4 dot into the chromium balance, we would have 0.0515 times 4500 equals 220.2 plus X5 M5 dot. So, we can also write a total balance for the treatment unit, which would be M2 dot equals M4 dot plus M5 dot. So, we already know M2 and M4. So, we can calculate M5 as 4500 minus 202.2, giving you a value of 4297.8 kilograms per hour. So, substituting the value for M5 dot in the chromium balance equation, we end up with X5, which is the mass fraction of chromium in the stream 5, which is leaving the treatment unit, as 0.002707 kilograms per kilogram. So, now we have the information about M5 dot, and we also have the composition of the stream, which is the mass fraction of chromium. So, we can also calculate the mass fraction of water, which would just be 1 minus mass fraction of chromium. Now, we need to identify the mass fraction of the chromium and the flow rate of the components in the stream 6. For this, we can choose the mixing point as the system, and we can write the mixing point balances. The total balance for the mixing point would be M6 dot equals M5 dot plus M3 dot. We already know that M5 dot is 4279.8 and M3 dot is 1500 kilograms per hour. So, using this we can calculate M6 dot as 5779.8 kilograms per hour. For the mixing point, we can also write a chromium balance. The chromium balance for the mixing point would be 0.0515 times M3 dot plus X5 times M5 dot equals X6 times M6 dot. We already know M3 dot, M5 dot, M6 dot and also X5. So, substituting the values, we would be able to get X6, which would be 0.0154 kilograms of chromium per kilogram. So, with that we have come to the conclusion of example problems related to systems with bypass. In the next lecture we will look at performing calculations for a similar system which is called as a purge system. Thank you and goodbye.